But happy Sunday, everybody. I hope that your day is going well so far and that your studying is going well so far for our final. Um, Before I get into what I'm primarily going to do for this review, which is a ton of problems, just a quick reminder about a few things. I'm going to do this session, I said until 5:30, but I've got a cushion up until 6. I do have to leave absolutely by 6 on the dot. I'm having dinner with a friend at 6:15. But then I'm coming back tonight after dinner. I'll be right back to my office for the whole evening. So if you feel like it would be a better option to study here on campus rather than at home or something, you certainly can do that. The library is also open 24/7 as well. So if you want to stay on campus but don't want to be in the shadows of my office, you certainly can do that as well. But anyway, that space downstairs will be open this evening if anybody wants to use it. Should be open all day tomorrow. I will be around a good chunk of the day tomorrow. Going to try to get in by 9:30, and I'm doing a study session tomorrow night at 7. But I pretty much have the whole day just devoted to taking questions, helping people get ready, answering questions, whatever I can do to help you guys feel really good to go for Tuesday. The last thing is, in terms of announcements, I mentioned it on Thursday in our last class, but just to reiterate it again, I'm giving my final at 2 different times on Tuesday. You can pick and choose when you want to come. You don't have to tell me in advance. You can just show up whatever time you want. So the options are, you can take the final at 9 a.m. on Tuesday. They're both in this room, or you can take it at 1 p.m. And I'm going to give an extra half hour or so for it. So you can, if you take it in the morning, try to plan to be able to go till 11:30 in case you want to have an extra half hour or so. And in the afternoon, a similar thing. I'll stretch it out an extra half hour for people to have a little bit of extra time on the final. The final is going to probably have like about 130 points on it, but I'm only going to be grading it out of 110. What that means is basically that you have a 20-point cushion before you even start. You can choose to skip something if you run out of time, or the other option is to just try and do everything, and then just know that you're already you have some wiggle room with points to play with here. So that's what will almost certainly be the case for the exam. So just so you know that that's coming. I'll give you the formulas for the Graham-Schmidt process. I'll give you the table of annihilators and integrals. I'll give you the differential equations for Newton's law of cooling and for the mixing problems if I decide to ask a question about those things. If I don't, then I probably won't bother. But at least for that much, I'll try to give you some help with those equations because I've traditionally always done that, and I'm not going to change my plan now. Okay? So anyway, so you have a choice here. If every single student shows up at one of the times instead of the other, I'll just spill over to a second room. I have still about 60 students between my 2 sections, so that obviously will be too many students to fit in this one room, but I will just spill over to a second room if I need to, and then I'll get another 20,000 steps walking back and forth between the rooms for all of those hours as well. So that could happen. Anybody have any questions about any of that? Logistics? Make sure you leave early enough in the morning or afternoon to get here on time. In fact, if everybody's pretty much good to go a couple minutes early, I will be happy to start you a couple minutes early. So Tuesday is not the morning to play around with traffic or to cut it close. So give yourself plenty of extra time so you can relax, get comfortable, and not be racing in and trying to think about math immediately. That's my advice. I'll probably show up on Tuesday pretty early as well. So if there's anything you want to hang out there in my office Tuesday morning before the exam, that should be fine. I won't have a lot of time once I go in. If you're coming in the afternoon, I won't have a lot of time because after the morning exam is over, I'll probably take a break for a bit. So try to get your questions answered before I have to go off to give my final. Okay, so that's the schedule. It's gonna be over with real soon. So last week we had a test on a lot of the material sort of from the last 6 or 7 weeks of the semester. We, of course, took an exam dealing with chapters 6, 7, 8, and 9. And part of those chapters included things like finding a basis for the kernel of the range. Solving a system of equations would come up regularly in that. What I'm trying to say is that a lot of the stuff did get covered already in the midterm just last week, which is good. Not that we don't need to look at it again, but I think at least we're not starting from zero. But I am going to probably start on this review today by really hitting some things that maybe have slipped through the cracks over, the recent time we haven't covered them as much. So I'm thinking about things like chapter 1, which has nothing to do with anything else really for the rest of the semester. And there's a couple of other topics like inner product spaces that we covered sort of in the middle of the semester that didn't really resurface again. So I'm gonna do, out of order as usual, a bunch of review problems, okay? And some of these are gonna come from the review session handout, but you know what? I actually went back and looked at, I already passed out 2 sample finals to you. You already have 2 sample finals, but then I went back and I looked at a third one that I've given in the past. I have like 20 of these. So I went back and looked at a third one and I was like, oh, that's got actually almost better questions than the review session. So I printed that out also, and I'll probably use some of those questions for this review as well. So it's going to just be kind of all over the place. But let me go ahead, and if there's no questions, logistically speaking, I'll jump in now. That sound good? Caesar.
Yeah. So when you're grading out of 110 only,
yeah,
with 130 points possible,
right?
You're not like, oh, this problem is better than this one. You're actually just adding them.
Yeah, I'm just going to add all the points. It used to be that I would say, I used to do something where I would do like, oh, I'll take your 10 best out of 12 problems, and I'd tell the students to cross off the ones they don't want me to grade. And what often happened was the students would cross off the wrong one. Like I looked at their work and said, oh, you would have gotten more points for that one, but you crossed it off, and now I'm grading this one, and you're not going to do as well. So instead of doing that, I just basically took that decision making out of your hands. All you have to do is do the best you can on everything, and you'll get all those points just added together. Yes, that's exactly right. So you can play it however you want. You can sort of think of it as, well, I can skip 20 points worth of stuff, or you can just say, I'm not going to think about that. I'm just going to try and get 130 points and, let the grading take care of itself, let the chips fall where they may. So, yeah. So try not to worry about that too much, but yeah, you can definitely get over 100%. I won't be surprised if somebody does. So that's just kind of the way I'm setting it up. Okay. All right. So let's try to practice a little bit on some questions that I think would be good to review. So I'm going to start from the review session. I'll try to give you the reference for where this is, and if it's something that you already have access to. So from the review session, I'm going to do problem number 9 first. So again, totally out of order. Sorry for that, but it's just the way these things have laid themselves out for me. So I have a differential equation here, guys. It's y prime minus 3 over 2x times y equals 6 times y to the 1/3 power times x squared times ln of x. Okay. So this is the problem, and we would like to solve this equation. Solve this differential equation. Okay, that means we're looking for what y is. We practiced a little bit on Thursday with the flow chart that I drew on the board, sort of all these questions that we should ask. You might remember at the top of the flow chart, the first question to ask is this a system of differential equations, or is it a single differential equation? Like, are there multiple unknown functions that you're solving for, or is there just one unknown function? And what would you say for this one? Is this a system of differential equations or a single differential equation? Aaron? It's just a single one, isn't it? Right? There's just one unknown function, which is y. If it was a system, there would either be obviously a matrix there for that system, or if there wasn't that, there would at least be multiple unknown functions whose derivatives were being referenced. So if we don't have that, then for sure this is a single differential equation. Okay, So if it's a single differential equation, the next question in the flow chart was, what is the order of that differential equation? Can somebody tell me what it is? It's just first order. Thank you. Yes, exactly. Just one derivative of y right here. So this is an n equals 1 problem. It's a first order differential equation, which means that I want to be thinking about chapter 1. Because chapter 1, the very beginning of the semester, is where we learned about first order differential equations. The next questions then is, well, is it separable? Is it linear? Is it Bernoulli? Or is it homogeneous? Those are the 4 kinds of differential equations that we learned about. And does anybody have a gut feeling about which of the 4 types we're looking at here? Yeah, this is a Bernoulli differential equation. Let me remind you the form of a Bernoulli equation. So this one is a Bernoulli equation, and I mentioned this on Thursday, guys. If you even just write that down, if you just write that down and you don't write anything else down, I will probably already give you a couple of points. Say it's a 10-point problem. I'll probably give you a couple of points for telling you that it's a Bernoulli equation. Actually, and I shouldn't have written n equals 1 there. I should have just written first order, because in a minute when I write down the form of a Bernoulli equation, I'm going to use an n for that. So the way this looks in general, guys, is it's y prime plus p of x times y equals q of x times y to the power of n. Right, so this is the notation for it here. And you can see that the equation that I am looking at is exactly in this form. There's a y prime, and then here you see the p of x. So in this case, the p of x is actually negative of 3 over 2x. Be careful about things like minus signs, because if those get thrown off, it can really throw off your work. The q of x on the right side, that's just all of the x stuff that's on the right side. I can see a 6x squared ln of x for that. And then what is the n value for this Bernoulli equation? 1/3, right? So y is being raised to the 1/3. So n is 1/3. Okay. So we have our Bernoulli equation. By the way, I'm putting some boxes around the important equations here. The change of variables is one that we just kind of pulled out of the sky back in chapter 1 when we talked about this. It's an equation that you should try to know, which is that u is equal to y to the power of 1 minus n. Okay. So in this case, this is a change of variables. The way we solve Bernoulli equations is we use this change of variables to convert it into a linear equation. So if the n is 1/3, then for this problem, u would be y to the power of 1 minus 1/3. In other words, y to the power of 2/3. This would be the correct power to use. And I like to get that written down, but we're not actually going to use this until much later in the process, right? So it's just good to write it down ahead of time so that when we come back to it later, we've already got it in front of us. And then the new differential equation that we end up with is the following. This is one that you need to know as well, guys. U prime plus the quantity of 1 minus n times p of x times u equals the quantity of 1 minus n times q of x. I'm going to put that in a box as well. Some of you probably already have flashcards with some of these important formulas on them, or you have some way of trying to quiz yourself on them again and again. For a couple more days, we need to do that, right? So if you, whatever you can do to learn these equations, because I will be giving you partial credit for writing all of this stuff down on your paper. So try to get those points as best as you can. Okay, so in this case, let's try to, and this equation, before I go on, this equation is always linear. So it becomes a linear equation because on the right-hand side, now you just have a function of x. There's no power of u over here, like there was a power of y originally. So this becomes a linear equation. And in a minute, we'll talk about how to solve a linear equation again. I like these Bernoulli problems because they do force us to remember how to solve linear differential equations as well. It's sort of you sort of get a big bang for your buck out of these kind of questions. Okay, let's plug in the 1/3 for n right here, and we've got our p of x and our q of x. I'm just going to substitute it all in here. So this is u prime plus 1 minus 1/3 would be 2/3 of the p of x, which is -3/2x times u. And then on the right side, 1 minus n is just 2/3, this time of q of x. Q of x was 6x squared ln of x, like that. So this is plugging everything in. Now I'm going to just clean it up a little bit. So I'll simplify. We have u prime. Notice the 2/3 and the 3/2 actually cancels, and we just end up with -1/x times u equals 2/3 of 6 is actually 4. So we get 4x squared times ln of x here. Right. Okay, so far, so good. This is the linear equation that we now have to solve. Okay, to solve the linear equation, we use the integrating factor. I'll just remind you about the integrating factors here. This is denoted with I, and the formula is that you take e to the power of the integral of p of x dx. So this is also going to go in a box. That'd be another really good flashcard item. Only thing I want to caution you about here, guys, is that the p of x that's in this formula is not the same p of x that we started with way back in the beginning. It's the new p of x that is in my linear equation. So I have to look here. The p of x is still in the same spot. It's just the coefficient of the unknown function, but in this case, it would be -1/x. So I is equal to e to the power of negative the integral of 1/x dx. Okay. And so this is just e to the negative ln of x. Couple of comments here. We don't need to put a plus c on the integrating factor when we do this integral. The other thing is some of you might be wondering why I didn't write down absolute value in here, because normally the integral of 1/x dx would be the ln of the absolute value of x. But actually, this problem, I probably should have just said it in the original question. The x should be greater than 0 anyway, because you can look back at the original problem, you're already taking the ln of x just in the original question here. So x cannot be negative even from the beginning, because you wouldn't be able to make sense of the equation. So we're kind of under the assumption that the ln makes sense here, and that would mean that x is greater than 0. Okay. Stop me if I'm going too fast, guys, because I'm in no hurry. I'm totally in no hurry here. Something like this, everybody needs to be able to simplify that. The e and the ln, of course, they normally would cancel each other out. But before you can do that, you have this little property of logarithms that you need to use, which is that you can put the coefficient in front of the ln upstairs as an exponent inside the function of the ln. So now the e and the ln cancel, and you just get 1/x for your integrating factor. Okay? So far, so good? Now, let's remember that what do we do with this integrating factor? What you do with it is you form the derivative of the product. I'll write down the general formula first here, guys. You form the derivative of the product of the integrating factor and your unknown function. So let's say your unknown function is u. And that needs to be equal to q of x times the integrating factor. And our unknown function at the moment is just u. Ultimately, we need to figure out what y is, but at the moment, I'm really just trying to solve for u, and I'll be able to do that if I just plug into this equation. So what am I going to have? I'm going to have 1/x times u as a product. and we're differentiating that. And then on the other side of the equation, we take q of x times I, and I'll remind you again, it's not the original q of x. It's the new q of x that's in our linear equation here. So this should be 4x ln of x. So it's really 4x, well, I can write it out. 4x squared ln of x, but then multiplied by I, we end up canceling one of the powers of x. So it just becomes 4x ln of x, just like that. So far, so good. Okay, now the next step is to solve for u. That's going to mean I have to integrate on both sides. So if I integrate on the left side, that will get rid of my derivative. So I'm just going to integrate here. So on the left side, when I integrate, I get rid of the derivative, and then I have to actually integrate on the other side. So I'll be doing the integral of 4x ln of x. I'll pull the 4 out of that, and then to integrate x ln of x, we've got our table of integrals. This one would not be that. I saw some people on the midterm last week actually trying to do integration by parts problems. I'm like, I haven't actually done one of those for you guys for almost the whole semester, so I'm probably not going to start now. So if it's something, it is true, you would normally integrate this using integration by parts, but you've got enough other things to do on this exam than working that out. It's much better to just go straight to your table. And we have the formula for the integral of x ln of x. It's number 8. Number 8 on the table. Now you do have to interpret the formula correctly. This is going to be with, there's a k value in the formula. And the k value that you have to use is a 1. So I'm going to, so it's number 8 on the integration table with k equal to 1. And what you get then is x squared over 4 times the quantity of 2 ln of x minus 1. Okay, and again, I don't need a plus c. I'm sorry, here I do need a plus c because I'm actually solving for the u. So let's do this. Let's put that plus c, doesn't really matter. So when I do this antiderivative, there is a plus c there, like that. Yeah, I've got the 4 kind of outside of everything. It doesn't actually matter. You could put this plus c totally on the outside in this case, and it would not matter. Okay. So there's the integral on the right side. If you wanted, you could multiply the 4 in, but you don't have to. Like, I'm okay if you just leave this like it is. If you multiplied it all the way in, it would maybe look a little nicer, but you don't have to do this. The other thing is, if you multiply it in, be careful because 4c should probably be relabeled as a c1. It's not the same constant anymore. So if you're going to do that, which you don't have to do, but if you're going to do this thing where you multiply through by 4, make sure that you remember to change the c to a c1. You with me? The other thing is, if it wasn't a 4, if it was, let's say this was a, I'm going to change this just for a second and then I'll change it back. If this was an x, and instead of leaving it the way it is, which is probably the better choice, if you decided I'm going to go ahead and multiply the x through, and so in that case you would have gotten x cubed here. In that case, what you have over here is cx, and that's not c1 because this is not a constant anymore. So I wouldn't want to relabel this as a c1. If it's a 4 times c, sure, that's just a c1. But x times c is a variable function of x. It cannot be changed. So just be a little careful, guys. If you're multiplying through by a constant, there's obviously no problem. Go back and change this to how it was before. But if you're multiplying through by something that's a function of x, you're going to have a problem with that if you relabel it as a constant again. Yeah.
So then would it be relabeled as C1x?
I would just label it as cx. You wouldn't need to even change the c. Yeah. Yeah, so there you go. So there is 1/x times u. So if I want to solve now for u, I just need to multiply through by x. So I'll just do that here. So just multiply everything through by x like that. And again, now see here, you could, just what I was saying, you could choose to multiply that x all the way through, but you should not change C1 to any other C2. It's just C1 times x if you do that. I personally would just leave it like that. I really would. I would just leave it like that. And remember now, guys, that u, so now we have one last thing we need to do. If we go back to the change of variables, u was expressed as y to the 2/3. So this becomes y to the 2/3 power right here, y to the 2/3 power right here. And so if I want to solve for y, which is ultimately the way my answer should be written, I would now want to take the 3/2 power of both sides. So how am I going to cancel a 2/3 exponent? By raising to a 3/2 exponent, because when you combine those exponents, those reciprocals cancel each other. So this would tell me then that y itself is this whole thing. I'm going to go ahead and just rewrite it the way it was. This whole thing to the 3/2 power. And that would be your answer for y. That would be the answer. Yeah. Okay. Good enough? Feel all right about that one? Okay. I mean, when you look at the sample test, you'll see that I definitely have Bernoulli equations represented pretty well in my materials here. So this is something to come back to. But honestly, the reason why I like these problems is that this one problem kind of reviews half of chapter 1. It's a lot of chapter 1 here because you're not only doing the change of variables technique, you're also reviewing how to solve the linear differential equations. And that's kind of an important thing to be able to do. So definitely a good thing to be solid with. Okay. If everybody's good on that, I'll move on to something else. Or so good? Okay. Where do I go to next? I have so many different directions I could go. Yeah, let's change gears completely. I'm going to jump around as we go through this session. I'll jump around a little bit. So let's go on to another problem. I'm not gonna number the ones that are not from the review session handout because you don't have access to these. These are just problems from another final that I've given. So I'm just gonna call this old final problem. And we're just gonna write it down here together. So what I'm gonna do is I'm gonna let B be equal to P2 of R. And I'm going to let S be the set of P of X, which is an element of V, such that P of 1 is equal to P of 2. And I have several parts that we're going to do here, guys. The first part is we are going to show that S is a subspace of V. Try to show that S is a subspace of V. Do you guys remember how we show subspaces?
Yeah, it's through closure under multiplication and addition.
Right, the vector space axioms are all hinging on the operations of addition and scalar multiplication. So we have to show that S is closed under addition and under scalar multiplication. That's exactly right. Okay, super. So I always like to do the addition first for some reason, but it doesn't really matter. You can do it in either order. Another way I could have asked this question, I could have said, is S a subspace of V? I could have made it into a yes and no question. Now, if I did that, then before I launch into checking the closures, Is there another thing that we sometimes do if we're not sure we have a subspace that we can kind of do right off the top without working too hard? Which way? Exactly. The zero vector check would be like a good one to do. By the way, does this pass the zero vector check? It does, yeah, it absolutely does, because if I take the zero polynomial, right? So if I graph this zero polynomial, this is a graph of it, guys. And if I plug in 1 into that polynomial, I get 0. If I plug 2 into that polynomial, I get 0. They are equal. So it does, so the zero function is in S. So this is just the zero vector check. Now, again, we don't need to do this zero vector check here because they didn't ask it. I mean, the zero vector check is never required. It's just that if you do the zero vector check and it fails, then you can just say, oh, it's not a subspace. But when the question is asked in this manner, when it says show that you have a subspace, well, now you already know that that zero vector check would pass because of the way the question is being asked. And if the zero vector check is just going to pass anyway, save yourself the time. There's no point in checking it if it's going to work. The reason to doing the zero vector check is that if it fails, then you quickly can say that you don't have a subspace. But here, we already knew that it was going to pass just because of what was being asked for. Show that it's a subspace. You guys following me on this? Okay, so let's try to check the closure under addition. What does this amount to again? We have to take two vectors that are in S to begin with and make sure that after we add them together, the result is still in S. So this is a little abstract, the one I've given you here, but I think we can handle it. We need two vectors that are in S, and we can introduce them however we like, or with whatever notation we like. I could call them f of x and g of x, or I could call them p of x and q of x, but I would definitely make sure that they actually look like vectors in S. So if we're not working with matrix, this would be a weird notation for this problem. So A and B, normally, if I'm thinking that, oh, those are matrices. Yeah, that's right. These are usually matrices. Well, we don't have matrices in this universe. This is not the universe of matrices. So I probably wouldn't use an A and a B. A better choice would be, yeah, to just go with something like f of x and g of x, elements of S. But you have to start with two things that are in S. And it's just abstract the way they've been written. Now I want to add these together, but before I add them together, I just want to write down what the condition is that membership in S gives us as a statement, right? So if f and g are in S, then we know that already that f of 1 is equal to f of 2. And we also know that g of 1 is equal to g of 2. That's what it means to be in S. The condition to being in S is right here, guys, right? When I plug in 1, the result is the same as when I plug in 2. Basically what we're looking at. So f of 1 equals f of 2 and g of 1 equals g of 2. By the way, these polynomials, they do live in the P2 of R. Do you think we should write them down as like ax squared plus bx plus c? We don't have to. Yeah, we don't have to. At least not the way this particular problem is set up. Notice that the condition for belonging in S doesn't get into the nitty-gritty of what those different powers of x are. So it wouldn't be wrong to do it, but I would not recommend expressing out your f of x into all these terms if the statement of what S is doesn't really require it. It doesn't really require. I would just leave everything kind of on this more abstract level. And now what I'm going to do is I'm going to look at f plus g. I want to add these two vectors together and see if the result is still in S. Now, when I add them together, I have to check. Does it satisfy this condition? So let's plug in 1. So we're going to take f plus g of 1. Does anybody have any idea what I can do with that?
You can do f of 1 plus f, sorry, g of 1 equal to 0.
Yeah, how about that? I can take f plus g of 1 and I can write it as f of 1 plus g of 1. Not necessarily equal to 0, but I can just write it as f of 1 plus g of 1. Absolutely true. And then does anybody have a suggestion what I might want to do next?
F of 2 plus g of 2.
Exactly. So f of 1 can be changed to f of 2. G of 1 can be changed to g of 2. Very good. So this becomes, f of 2 plus g of 2. And anybody want to finish this off? One more step we need to do here. We started with the quantity of f plus g of 1. What do we want to end up with?
Can we say that 0 plus 0 is?
There's no 0 here.
Oh.
There's no 0 here at all. Okay, the condition doesn't have a 0 in it. Aaron?
Can you just say f plus g 2?
That's right. That's right. I just want to go back to making it look like the f plus g again. Yeah, so that's it, guys. That's it. That's the whole thing. F plus g of 1 equals f plus g of 2. And this implies that f plus g, I guess I can call it f of x plus g of x, sorry. F of x plus g of x is in S, and I'll put my check mark. Remember, guys, that this is important that you conclude the statement with this condition here. So the sum of the two vectors is in S. If you don't say that at the end, usually my red pen comes out. So not a huge loss of points, but you don't want to lose those points. So just be sure you add that at the end, that you're taking that the result of adding the vectors together is back inside of S again. Is everybody comfortable with that? You guys did pretty good. I didn't have to really work very hard there. I just had to write down what you guys told me to write down for the most part. So that's always a good sign. Excellent. Yeah, so this is where the meat of the calculation is, and we don't need to get into the nitty-gritty of the different powers of x at all. Let's go on to the scalar multiplication then. By the way, if the closure under addition happens to fail, it's obviously not going to fail on this problem, but if the closure under addition happens to fail, then you don't have to do anything else with the scalar multiplication. You can just say it. Oh, it's not a subspace, and you're done. But here, we do need to go on. And what I like to do here is grab a scalar. Anybody remember what letter I use for my scalar? It's usually a k, right? So k is an element of the real numbers. And I'll just say f of x as above. So we'll just use the same f that we were using earlier, so we don't have to like start from scratch again completely on that. And what I want to do is I want to take the scalar multiplication of k times f of, sorry, it's actually, so I want to take the scalar multiplication of k times f, and I want to check, I want to ask myself, when I plug in 1, is it going to be the same thing as if I plug in 2? So I can put 1 right here. So this is k dot f of 1. And any thoughts about what I might do with that expression for the first step here?
Take up the k.
Right, exactly. I want to get the k totally on the outside of everything. So let's just do that first. That's certainly allowed. So it's just k times f of 1. And then we already know that f of 1 can be changed to f of 2. So let's do that. And then we just go right back where we came from. But now we have k times f of 2. And so that's looking pretty good. And so that all of that then shows that k times f of x is in S. Don't forget that conclusion there at the end. So that means you do have closure under scalar multiplication. If you stopped right now, I would accept that as an answer, but just since you guys are still studying and just to make sure we understand what we actually did here, we are now able to conclude that S is a subspace of V. So that we can do. All right, excellent. All right, let's do a part B. That was only part A. Now that we actually do have a subspace, it would be natural for me to follow up and say, well, let's find a basis and a dimension for that subspace. So part B here is going to be find a basis / dimension of S. Try to find a basis and a dimension for S. Question, go ahead.
I remember we had a big discussion about the conditions of the initial problem in part A for the dimension. So if it has an initial condition, can we knock down the dimension by 1?
You pretty much, just as a rule of thumb, you know what the dimension of V is. By the way, what is the dimension of P2 of R? 3, right? So as you add conditions here, you are of course going to knock down the dimension. And so what Oscar is remembering is that, okay, so for each extra condition that you have, the dimension from V will get knocked down by 1. And here we have only one condition. So if you were saying, if your thought is that the dimension of S would be only 2, so the dimension of V is 3. So it would be very good intuition that the dimension of S would be 2. But if you just wrote that down with no justification, I wouldn't give you anything for it, right? It's actually also, it's not really a rigorously correct thing. I could give you 2 conditions here that were actually interdependent on each other. So even though it looked like it was 2 conditions, it actually, when you boil it down, it was really only 1 condition. So then if you use that theory that you could start subtracting however many conditions you have, you could get into trouble because the number of conditions that you see could be like an illusion. It's like, oh, I see 2 equations here. Oh, but actually the 2 equations are kind of more or less the same. And so you can get into trouble if you just kind of go blindly through some kind of rubric of that nature. So the better thing to do here is actually going to be to just find the basis, since they're asking for that anyway. Find the basis, and once you have the basis, count how many vectors that you have. Okay. If you get the basis wrong, but then you answer the dimension correctly for what you wrote down, I'll give you full credit for the dimension part. So again, it's not an all or nothing proposition here. Okay, so how am I going to figure out a basis for S here?
Would you write down the general formula?
Yeah, so at this point, even though I made great pains to avoid it in the first part of the solution, for this part of the problem, I really do need to write out my quadratic polynomial, right? So what I'm going to do here, guys, is I'm going to write out my f of x as ax squared plus bx plus c. Now, as it turns out, that's not precise enough to capture what S is. This would be the general form for a vector in V. But this does not include the condition that when I plug in 1, it should be the same as when I plug in 2. So the condition here is really important, right? This thing. And a lot of people, when I ask this kind of a question, they put that f of x down and they just use that. But actually, if they do that, they have completely ignored this condition, which needs to be put into it. So what you're going to want to do here, guys, is you're going to want to actually plug in 1 for x and plug in 2 for x and set them equal to each other, just like that equation tells us to do. So if I do that here, so note that f of 1 is equal to, well, it's just a plus b plus c. Right? And f of 2, I plug in 2 for x, I get 4a plus 2b plus c. What's going to happen is we're going to create a constraint equation for the a, b, and c variables. These two are supposed to be equal to each other. Right, so maybe I'm going to do a little curved equal sign here. I'm going to set those equal to each other. And if I do that, then, 4a plus 2b plus c is equal to a plus b plus c. Cancel the c. And then I've got, a very easy equation to simplify. 3a plus b equals 0. If you really want to, of course, you can put this into a matrix. You can, I know this seems silly when you only have one equation to make a matrix out of it, but you've got your variables a, b, and c here, and this just helps me remember that I have some free variables and I have some pivoted variables. So the a variable is pivoted, it's my leading variable, and the b and the c are both free, okay? So you don't have to change these letters, but I like to. So I'm just going to use R and T, which are my two favorite letters to use for free variables. And that's going to be my B and my C. And then when I solve for A, from the equation that I have, I just get negative 1/3 of R. Okay. Now it's tempting to take the A, B, and C here. It's very tempting to take that and then just draw it into, a vector like this. It's tempting to do that, but guys, we need to remember that we're not in the universe of R3 here. We're looking at polynomials in this problem. So what we need to actually do is take these expressions for A, B, C and put them back in for the places they occur in the f of x. Right, so then I'm going to come back to my f of x now, and I have a, which is negative 1/3 of r, being multiplied by x squared, and then the b, which is r times x, and then the c, which I've changed to t as my constant term. And now what I've done is I've written down the general form of a vector in S. It's not just a vector in P2 of R anymore. This is a vector in S. If you plug 1 in for X, you should get the same answer as if you plug 2 in for X. Okay. What's my next step going to be? That's right. We've done that for weeks now. We take this form and we bust out the variables. BOTB, right? Bust out those variables. When I bust out the, and then I'm just going to, well, I guess I can bust them out right here. So I'll bust out the R. By the way, remember that X is not one of the variables. X is actually part of the object of the polynomials. The variables are the R and the T. When I bust out the R, I get negative 1/3 of x squared plus x. And when I bust out the T, I just get a 1. So I think I did that correctly. And so this is the same f of x, but with the two variables busted out. And what you do is you write down your basis by just making a list. I use the squiggly braces, and I just make my list of my vectors here. Negative 1/3 x squared plus x, comma, 1. So that's your basis. That's going to be the basis. Does that look all right? And now this does confirm, as was already mentioned, that we just figure out the dimension of S by knocking down the dimension of V by 1. So it goes down from 3 to 2 in this case. And that's because there's two basis vectors that are there. There's two basis vectors there. Good enough? Questions on that? Seems okay. So this is also something that is almost guaranteed for the exam. It might not be with polynomials. It might be with matrices. It might be with slots. It might be with calculus functions. We've had several different universes that we've played with. But this is worth practicing again. So you've seen one here. Go find a similar problem in the sample final and see if you can do it. And I promise it'll be very helpful to do that.
Um, we also had another discussion about isomorphism,
Mm-hmm.
kind of communicating within different spaces.
Right.
Would you give partial credit for that, or would you want it in the specific?
If you tried to like turn this whole problem into, let's say R3, because after all, R3 is isomorphic to P2 of R. So if you basically said, every time I write down ax squared plus bx plus c, I'm just gonna start writing it as ABC. And if you started just changing the notation in that fashion, I would give you some points for that, but it would not be an ideal way to work out the problem, and you would definitely not get full credit if your final answer was written this way. That's exactly what I'm just saying right now, is that we have these different universes, and you need to be prepared to do these problems in any of those different universes that we've used. Polynomials is a common one, but so is matrices, so is just Rn, and so is calculus functions. Those are the universes we've usually seen. I know there was one like this back on the second midterm. I know that there's one on the sample finals. So as long as you're doing what I've already suggested that you do in terms of studying for this exam, you're going to run into more of these, and that'll be good, because this is very likely to be asked. I'm trying to start off today, guys, with things that are absolutely high on the priority list. Okay, let's do another one. Unless there's any other questions here. So far, so good? Okay. So I'm gonna do another problem from an old final. So this is just kind of out of the blue. You haven't seen this one before, which is probably a good thing. Give you some fresh practice here, guys. So if the set of V1, V2, V3 is a set of vectors in an inner product space B. So I just reminded you before I finish writing the question down, an inner product space, it is just a vector space. It's a vector space that has an inner product defined on it. The purpose of that, remember, is to create a geometric framework for the vector space. So normally in a vector space is normally a purely algebraic structure. You have addition, you have scalar multiplication, you have a bunch of rules. It's all algebra. After all, it's part of linear algebra only. But mathematicians have recognized that there might be a benefit to creating a geometric perspective on that vector space concept. And so that was what was called an inner product space. It allowed us to do things like angles between vectors, norms of vectors, orthogonality of vectors, stuff like that, that you can do. So this was the reason we did this. Now I'm going to give you some conditions here. This is a set of vectors in an inner product space such that the inner product of v sub I with v sub j is equal to I plus j. Okay, and then I'm going to ask you to compute something. I'm going to ask you to compute the number, which is going to be 2 times v1 minus v3, inner product with 4v2 plus 6v3. Okay. So that's the question. When you take the inner product of two vectors, the answer should be a number. So we're just looking for a number, a numerical value here. And this kind of a question, it may look very computational, but it's actually, I would say it's more conceptual really, because you just need to manipulate this expression using the axioms. And one of the things I wanted to make sure that I got down on today's review session is what are those axioms again? Because this has been a few weeks. So there are 4 axioms of an inner product here, and I just want to go over them. Before we solve the problem, I just want to write down those axioms for you, because we're going to use these axioms to help us do this computation. So the first axiom is that if you take the inner product of any vector with itself, that the answer should always be at least 0. You should not get a negative value. It is a number, but it should not be a negative number. So when I take the inner product of a vector with itself, that should be the case. Now, here, I'm not taking the inner product of a vector with itself. These are 2 different things here. So if we ended up getting an answer that was negative here, that would not freak me out, because I wouldn't be expecting this to have to be positive in this case. If it's the same vector in both slots of this inner product, then it should be greater than or equal to 0. And I'll add a little bit more here, guys. It should equal 0 only when the vector itself was 0 to begin with. So that's kind of a little follow-up of the first axiom. Okay. Does anybody remember what the second axiom was? This goes back to March. I know it's been a while. Aaron? Commuting the vectors. Yes, that's exactly what you would call it. Yeah, so the inner product of V with W should be the same as the inner product of W with V. That's exactly right. Okay, so you can switch the order of the vectors. And then, does anybody remember the third one? Bishway?
Respects scalar multiplication.
Beautiful. It respects scalar multiplication. So if I had, let's say, K times V, and I wanted to take the inner product of that with W, then I can just pull the K out. So the K comes outside, and then we have the inner product of V with W from there. Exactly like that. That looks great. And then finally, the fourth one, sorry?
No.
Go ahead. Please.
You can, if you're adding 2 vectors,
Uh-huh.
you can add it with the other vector. For example,
I would just say that the inner product respects addition.
Yeah.
So it respects scalar multiplication, which is number 3. And then number 4 would just, I would probably write it like this, guys. If I add V1 to V2 and I do inner product with W, then this is just the same thing as the inner product of V1 with W plus the inner product of V2 with W. Yeah. So that's the fourth one. The third and fourth axioms are really, if you think of them together, they're just saying that the inner product should respect the vector space operations, right? So they respect the vector space operations, yeah. And the second axiom, the one that says you can switch the first and second slots of the inner product, the second axiom actually allows you to apply the third and fourth ones in the second slot instead of the first slot. So you might notice that the K is in the first slot here. It's not in the second slot. And the adding is going on in the first slot here, not the second slot. But what if it was? After all, I see addition happening in the second slot here. Well, the thing is that the second axiom says, yeah, you can also apply those same properties 3 and 4 in the second slot instead of the first slot. Back when I gave my lecture on this, I actually showed through the use of these axioms that that's true. If you want, you can just imagine that there's really an axiom 5 and 6 as well. Axiom 5 says you can pull constants out of the second slot. Axiom 6 says that addition is respected in the second slot. So there's really additional things that you can use. Anyway, you won't have to explain any of that to do this problem, but I just wanted to review it. I mean, I could give you a formula and ask you to verify the axioms. I'm not likely to make you verify everything, but I might give you a choice or something like that. And pick your 2 favorite axioms and verify them or something like that. That would certainly be a reasonable question. This problem is not asking us to verify these axioms. We're already assuming that we have an inner product space with a valid inner product. So we can just run with that. We can just take this formula, which is basically being given to us, and we can use it to crunch out the calculation. Yeah, okay. So let's do it. Let's try to solve this problem now that we've written down these axioms. So what you're going to want to do is, let's just write it down again. So the inner product of 2v1 minus v3 with 4v2 plus 6v3 is equal to, and what we're going to do here, guys, is we're going to essentially use the third and fourth axioms over here to FOIL this out. You can just literally think of it as a FOIL. So, you know, you can split it all apart. So I can go, you know, inner product of 2v1 with 4v2, right? And then I can go plus the inner product of 2v1 with 6v3, right? And then I can go plus the inner product of negative v3 with 4v2. And then finally plus the inner product of negative v3 with 6v3. So that's literally like more or less foiling it out. And as of so far, I didn't factor out the scalars yet, but I'm going to do that next. So I'm going to go to the next step. In the next step, I will factor out the scalars. In this first term on the right side, I have a scalar of a 2, and I also have a scalar of a 4. I'm going to pull them both out. And I can just do that all at the same time. So this is going to be 8 times the inner product of v1 with v2. Just going to write that directly. Okay. And then on the second term, I have a 2 and a 6. I'm going to do the same thing. I'm going to pull that out as a 12 times the inner product of v1 with v3. And then I have a negative along with a 4. I pull both of those out. I get a minus 4 times the inner product of v3 with v2. And then finally, I can pull out a negative and a 6. And I have inner product of v3 with v3. Kind of running out of room here, but hopefully that's all visible and reasonable for you guys. So we're almost done. The only thing left to do is to put in the numbers for what each of these inner products is. But that's what they gave us the formula for in the box here, right? In this box, they told us how to evaluate the inner product of any one of those VI and VJ terms. Yeah. What does it tell us to do? It tells us to just add up the subscripts. Just add up the subscripts. So in this case, I'm just going to, 1 plus 2, that gives me 3, right? And then the next one is 12 times, and then I have 1 plus 3, which would be 4. Let's come over here. So 12 times 4, and then minus 4 times, let's see, 3 plus 2 would be 5. And then minus 6 times 3 plus 3, which would be 6. Okay, so as we said, this is just going to be a number. At the end of the day, we're just coming up with a number here. This is going to be 24 plus 48 minus 20, and then minus 36. So, and I believe, if I'm not mistaken, this is going to be 16. Yeah, so this adds up to 16. So in this case, it did come out to a positive number, but if it had been negative, it would not have been, there would not have been anything wrong with having a negative answer here, because these two vectors are not the same vectors. Yeah. So that's good to know. Okay. Questions on that? So far, so good? Okay, fantastic. While we've got those axioms up here, why don't we do another problem on this same topic for a minute while I'm thinking about it? I just have to find my questions here. Yeah, okay, let's do another problem that would be on this same chapter while we're thinking about it. So how did you guys do on those two homework problems that we turned in yesterday? Was it okay? Not too bad? That non-homogeneous linear system of differential equations, we have that long process to do, but it's at least it's just plugging and chugging. It's not too crazy. Okay, I'm gonna do number 11 off of the review session handout now. So this is off of the review session handout. Verify any two axioms of an inner product for B equals C of 0, 1, and the inner product of F and G is the integral from 0 to 1 of T times F of T times G of T times dt. Okay. This one is not quite the standard inner product on V. So I might remind you guys that the most famous example of an inner product is just your regular dot product. But that's for Rn, right? So in Rn, we have our regular dot product that we can use. This is probably the second most famous inner product, but it applies in this universe of calculus functions. And normally, the second most famous inner product does not have that t there. It's just f times g. So I'm throwing in a t into the formula here, so it's making it not quite as standard, but it's still going to work. It's still going to be a valid inner product, and they're just asking us to verify any two of the axioms. So we can take our pick. Which ones do we want to do? I don't know if I'm going to do all four of these guys, but I'll at least show you a little bit of this, just to give you the idea, okay? So let's just see if we can do this, and then we'll have a follow-up. Once we know that this is a valid inner product, I will ask you a nice follow-up question as well. So we can just go through these axioms. I like to start with the first axiom. And again, I'm just using the axioms from over here, number 1 through 4. So let's use those axioms here, guys. The first axiom involves the inner product of a vector with itself. So I would like to convince myself that this will be greater than or equal to 0, but let's use the formula to derive that. If I use the formula, everywhere I see a g, I'm just going to put another f. So my integral becomes the integral of t times the quantity of f of t squared. Okay, and the question is, will this be greater than or equal to 0? Well, when you square something, of course, it's already greater than or equal to 0. Now, when I multiply that by something else, I have to wonder, well, could it now become negative? But the t is limited to the domain of this integration. The dt is my dummy variable of integration, and it's ranging only from 0 to 1. So you're only looking at the part of of the x-axis, so to speak, between 0 and 1, and during that interval, that will be greater than or equal to 0. So I'm just going to go ahead and write that that is greater than or equal to 0. If you just wrote that down and you didn't say anything else, I probably would still take it. But just to be clear, I'll just add a little bit here. I'll just say since t is between 0 and 1, and f of t squared is greater than or equal to 0. So it's pretty obvious that you're multiplying inside this function, you are multiplying together two things that are both greater than 0. And so the result is greater than 0. Remember, guys, the integral of a function is always representing what? It's the area under the graph of the function between, in this case, 0 and 1. And as long as that function is above the x-axis, the integral will count that as positive area. And this is definitely above the x-axis, guys, because t is a positive value and f of t squared is also positive. So everything here is positive. And so this is certainly greater than or equal to 0. And the only way it could be equal to 0, so equals 0 only if f of t itself was 0. What I'm trying to say is that if f of t was somehow positive, was not 0, if it was, not 0 somewhere, then you would get actually a positive value out of this. Somewhere the graph would be strictly above the x-axis and your integral would have been positive. So the only way that this could have actually given me 0 area under this curve is if the function was 0 to begin. I'm saying a lot, I'm not writing a lot down. In this case, you can go with what I'm writing more than with what I'm saying. Just trying to explain it for you guys, but honestly, for a write-up, this would be more than enough. Okay? The rest of the axioms, I think, are actually easier to explain. Like axiom 2 is really easy. The inner product of f with g. So this is just, again, using the formula that was given to us. It's the integral from 0 to 1 of t times f of t times g of t. And all I have to do, if I want to show that it's the same, if I switch the order, what am I going to have to do here? Just switch the g and the f directly inside the integral. That's exactly right, guys. So this is just t, g of t, f of t. Yeah, and then you say, oh, okay, well, that's just the same formula with the f and the g in the opposite position. So that's very straightforward. That's very straightforward. The third axiom, I think I'll stop after the third one, but I'll do the third axiom here. If I took k times f, inner product with g, if I had something like that, then this would be the integral from 0 to 1 of t times kf of t times g of t dt, right? And so you've got this constant k that's part of the integrand of the function. What are you going to do with the k here?
Take it out of the integral.
Take it out of the integral. You can do that, right? With constants. Constants can always, you've been doing this since calculus days, right? So you can always pull constants all the way out of your integral. So I would just do that. So you just get k times the integral of t times f of t times g of t dt. And that's just k times the inner product of f with g. So check that one off. So I've now checked 3 of the 4 axioms. Integration also respects addition, so I won't bother to write that one down. We'll save a little bit of time here. But the 4th axiom would go through without a problem as well. Questions on that? Okay, well, I have a follow-up here. If we're good on that, I do have a follow-up. Now we have a valid inner product. And I would like to use it to now actually do a geometric or a geometry application. So I would like to, I'll just call this a follow-up to the same. It's also on the handout, so I'm just following up with what's on the review sheet. The follow-up question is basically just going to ask you to find the angle. Find the angle between f of x equals 12x squared and g of x equals 2x. So we could just ask something like that, I suppose. Be a reasonable enough question. Does anyone remember the formula for the angle?
Would it be the inner product over the equation, the given equation?
So the theta would be, does everybody else want to help them out? The reason that like it sometimes puzzles me that it seems like when I teach this class, a lot of times people don't know this formula, but the reason that always bothers me is because it's actually just the same formula that you used in calculus when you were doing the angle between vectors in R3. The cosine of theta, so this is in terms of a cosine function. So I'll write theta as the arc cosine of, and then if you remember from calculus, you just take the dot product of your two vectors and divide by their norms. Now the dot product, of course, here I'm not really going to call it a dot product, I'm going to call it an inner product. So I'll say inner product of f and g. And then in the denominator, I'll put the norm of f and also the norm of g. So that all gets put downstairs inside of that. So it's the same formula that you would have had in your Calc 3 class. Right, same formula as from your Calc 3 class. So this is the formula for the angle between two vectors, and I'm just going to calculate now the things that we have here. So for my solution, I have to calculate obviously the inner product of 12x squared with 2x. And well, if I want, I can pull the 12 and the 24 out. You don't have to do that, but I guess I will. It's easy enough. So you can pull those coefficients out since that's one of the axioms. And then the inner product of x squared with x. Let's just look at that, guys. That's going to be an integral from 0 to 1. I'm using the same inner product, right, that we had in the first part of the question. So it's still an integral from 0 to 1 of t times f of t, which is really just t squared, and then times g of t, which is just t. So if I just replace x squared with t squared and x with t, sometimes people get confused. Like, should this integral be with t's or should it be with x's? I've seen that confusion before. The fact of the matter is it doesn't matter because you're just looking at a dummy variable of integration. There's a dt on the end of that. Right? It's just a dummy variable of integration. So it doesn't matter whether you call it x's or t's, but the one thing you really don't want to get confused with is if you put both t's and x's in there. If there's x's and t's mixed together here, that's really a potential to be confusing. So it's better to just go with one variable or the other. I'm going to go with t's. You can see that we're really just integrating t to the fourth. So the antiderivative of that is t to the fifth over 5. I end up evaluating that from 0 to 1. And as you can see, this just gives me 24 over 5. Okay, so that's one of the values that we needed to calculate. Another value that we need to calculate is the norm of each of the functions. So let's work on the norm of 12x squared for a minute. You guys remember the formula for the norm of a vector?
The square root of the inner product of its of that.
Exactly, it's the square root, very good, it's the square root of the inner product of the vector with itself. You just take the inner product of the vector with itself here. So just in general, let me write it somewhere that we can all easily see it and remember it, because this one is important in this chapter on inner products. The norm of a vector, guys, it's always the square root of the inner product of that vector with itself, just like that. So that's a good one to know. It's a good one to know. So I'm going to use that right here to do this calculation. Okay, so let's do that. Let's take the square root. I'm going to pull both of my 12s outside, which is really just going to give me a 144, and then times the inner product of x squared with x squared. The square root of 144 is actually just 12, so I can go ahead and just think of it that way, times the square root of the inner product of x squared with itself. And now I'll come up here. So this is 12 times the square root of, and then underneath the square root, I now have to do this inner product. That would be integrating from 0 to 1 of t times f, which is t squared, and g, which is also t squared. So you would just get that integral right there underneath that radical. And so as you can see, I'm integrating t to the 5th. This is 5 powers of t right here, gang. 5 powers of t, so when I integrate that, I just get t to the 6th over 6 from 0 to 1. And so that's just 12 over the square root of 6, I think. I did that right. Hopefully. And there's nothing wrong with leaving it like that. I guess I'll just leave it like that. We'll leave it like that for now. No big deal. That's the norm of the first function. And then I also have to do the norm of the second function. So a little bit more room here. So far, so good. No questions yet? This is totally computational. In fact, most of this chapter is really very computational. So I think that's one thing to keep in mind, is that this is usually not terribly difficult conceptually. It's mostly just being willing to brute force through the calculations. We do need to find the norm of our other vector, which is the 2x. So that's going to be the square root of the inner product of 2x with itself. I'm going to go ahead and pull out the 2 times 2, and that becomes a 4. That's the square root of 4 times the inner product of x with itself. The square root of 4 is just 2. So now we just have 2 times the radical of the inner product of x with itself. And underneath that radical, I'm going to integrate from 0 to 1 of t times t times t. So the f and the g here, they're both just x, which turns into t. Again, try not to mix x's and t's inside of here. That's the one thing that can really make this confusing. So to help yourself out, just, I don't really care which letter you stick with. These could all be x's instead of t's, but they should not be mixed together. They should be all separate. Okay, so what do we have here? This is the square root of 1/4 of t to the 4th, yeah? From 0 to 1. And that just gives me 2 times the square root of 1/4. Square root of 1/4 is actually 1/2, so we just get a 1. It's just a 1. That's not so bad. Okay, so using the fact that that's a 1, and then coming back to our formula for theta, theta just becomes the arc cosine of the inner product of the 2 vectors, which was 24/5, and then divided by the norm of the first vector, which is 12 over radical 6, times the norm of the second vector, which was just 1. If you left it like this, I would take full credit for that. That would be full credit. This one does not need to be simplified. First of all, you're not going to have a calculator anyway. So if you're not using a calculator, there's really not much point. You're never going to get to the final answer with pencil and paper. If you wanted to simplify it, I mean, I totally recognize that this is fractions of fractions, which is not really considered to be simplified very much. If you wanted to simplify it, you certainly could, but you don't need to. Definitely don't need to do that. Questions here? So find the angle between two vectors. Got to know this formula. If you write down this formula, you'll get points for that, even if you don't do anything else. So that's and this one's an easy one in my opinion, because it's really just a repeat of something from Calc 3. It's not really a new formula. Okay. Sweet. Anything else on that one? For now? Okay, just gonna keep plugging away. About amazing how fast the time goes. Already over an hour into it, but we're covering a lot of good ground.
Actually, I have a question.
Yeah,
If you're not given like the initial function, how would you go about?
eating this.
Yes,
Uh-huh.
how would you go about finding, I guess, an angle or
Can't do it.
can do it?
Can't do it. You can't solve these problems without having an inner product. Now I did mention there's one scenario where they sometimes won't give you the formula, and that's if it's vectors in Rn. So this is not Rn, as you can see, this is a different vector space. But if the vector space was Rn and they asked you these kind of questions, you could just assume that it's a regular dot product. And just use that dot product formula. But in any other scenario, they would have to give you the formula. Yeah, absolutely. Actually, that reminds me, I wanted to say one other thing over here. Do you guys, so you see that this formula was given. If I changed the limits, let's say to 0 to 2, that would actually change all of these numbers over here, right? It would totally change your calculation. The actual answer is highly dependent on the formula that you're given. Because when you start doing those integrals, then instead of evaluating 0 to 1, you'd be evaluating from 0 to 2. And it would be a totally different set of numbers. So just keep that in mind that, you know, this limit of integration makes a big difference. The other thing is, if you're not careful, so let's change it one more time. If I change the limits from -1 to 0, I actually did this in one of those extra credit videos that you watched. If I change the limits to going from -1 to 0, you actually get something that no longer satisfies the axioms. This is actually a illegal formula for the inner product, because if you change these limits from -1 to 0, now your t is from -1 to 0, which means it's negative. It's being multiplied by this positive part, and it results in a negative integrand, right? The integrand would be negative, and the first axiom would not give you greater than or equal to 0. It would give you less than 0 in that case. So it doesn't take much to tweak a valid formula into an invalid one, or vice versa. So you really have to look closely at it. But, you know, obviously the question will guide you. It'll say something like, you know, verify. It might ask you, is it a valid inner product? That would be the other way I could have asked the question. Is it a valid inner product? Of course, if the answer is no, if it's not a valid inner product, then you're not going to get any follow-ups because you can't do anything with it, right? So there won't be a follow-up in that case. But if it is a valid inner product, then I might ask you to verify the axioms and maybe do something with that formula. Okay. Good thoughts all around. Any questions about that? Yeah, Bushra.
Is there any conditions other than the ones that you mentioned where the inner product won't be validated?
Besides just changing the limits? For this particular example, not really. I mean, I could also mess around with what's being integrated in here. And that could play into it as well. It's one of those things, I think, where like I could like tweak this 1,000 different ways. And it's not my recommendation that you spend the next 2 days just studying every possible like tweak that I could do to this. What's more important is knowing the 4 axioms and knowing your game plan. My game plan is gonna be, all right, I need to either verify these axioms, or if there's a question about whether it's valid, I need to see whether they work or not. And to have that game plan in mind and being able to work with it is more important than, trying to, I guess, figure out like, how could this be tweaked 100 times? Because at the end of the day, I'll give you the question, and if you've got the strategy and the game plan in place, you should be good. Yeah. Other questions here? These are good questions. Yes.
As far as like the game plan goes, would you say that verifying the first axiom would be the most difficult, therefore the go-to to do it, to prove everything else?
Yeah, I mean, I usually, for a lot of these formulas, it's the first axiom that is the crux of the whole thing. If the first axiom, if any of the axioms are going to fail, a lot of times it's the first one, but that's not always true. It's actually possible to create formulas where it's one of the other axioms that fails. So, but I like to just go in order. I would not recommend just mixing it up for no good reason, unless you could really see something easily that was wrong with a different axiom. I would probably just go in order. Yeah, because the first axiom is as likely as any of them to be the one that's going to be the problem. Yeah, definitely. Okay, let me erase a little bit here, and then let's do another problem. Everybody doing okay so far? All right, great. Okay, so let's do this, guys. So this is also off of an old final. It's another problem that I used in the past, but which is not part of the stuff you guys have. Let's solve x prime equals a times x, where capital A is the matrix 5, 0, 7, 0, 6, 0, and 1, 1, and negative 1. Okay. Now, I realize that this is kind of a more recent topic, so you might feel like, well, we just studied this. If that's true, if that's the case, that's great. Maybe this is something that doesn't scare you too much. It probably shouldn't, to be honest, because it's just a system of equations, right? Going back to our little flow chart. Is it a system? The answer is yes, because there's vectors in a matrix here. So it's a system of equations. Is it homogeneous or not homogeneous? Which one is it?
No.
Is it homogeneous or is it not homogeneous?
It is, because there's no B.
There's no B there's no B on the right-hand side. So remember on Thursday, we talked about, what happens if you add a B here. This is not homogeneous, but if there's no B there, then it's homogeneous. So it's a homogeneous system. So what's our method for solving it? Like, how do we start this off? Exactly. We got to find our eigenvalues and eigenvectors. We're going to need to figure out whether this matrix is defective or not defective, and so on and so on. So there's a lot to this, but let's just see what the eigenvalues are first. So I'm going to subtract lambda off of the main diagonal. And so I'll have this kind of a 3x3 determinant. And how would you recommend for me to do this determinant? I'm going to expand using cofactor expansion. And of course, in theory, I can use any row or column, but which one would you suggest here? row 2, right? Row 2 because there's a lot of zeros in the second row. It has more zeros than any other row or column. So you really want to look at your matrix carefully and pick the right row or column to do the expansion. So in this case, I would use row 2. I've got my 6 minus lambda here in the middle. And then when I cross that row and column off, I get the determinant of the minor that consists of the 4 outside corners of the matrix. On the 4 outside corners, I have 5 minus lambda times -1 minus lambda, and then -7. Okay. Now remember that the thing you want to try to do here is get it factored. You don't want to multiply it out. You want to factor it, which is kind of the opposite. So the 6 minus lambda, I'm not even going to mess with that. I like having that on the outside. And then the part that's in these brackets, I will multiply out so that I can get a quadratic equation out of it. So I have a lambda squared, I have a -5 lambda and a plus a lambda, so that's a -4 lambda. And then a -5 and a -7 is actually a total of a -12. Okay. So now I have 6 minus lambda times, this actually does factor nicely. It's just lambda minus 6 times lambda plus 2. If you didn't see how to factor that though, you could always use the quadratic formula to get the lambdas, and that would be fine. But as you can see, the lambdas that we've ended up with are 6, 6, and -2. 6, 6, and -2. And I would say on the midterm last week, most people got most of the lambdas right on most of the exam. On the problems where somebody didn't get the lambdas right, I had got out my red pen. Actually, it was a black pen. But I got out my pen and I basically wrote a note, did you check the fun facts? Because that's what you should do. If you're getting these lambdas wrong, it's really going to be annoying for you to get the rest of the solution. So to make sure that these lambdas are right, add up the main diagonal of your matrix here. It adds up to 10. And make sure that your lambdas are adding up to 10. Okay, and they do here. So this is at least reassuring. You can also use the fact that when you multiply the lambdas, which in this case is -72, it should agree with the determinant of this matrix. And you can check that too. Okay, so by using cofactor expansion on the middle row, it's very easy to check that the determinant of this matrix is -72. So our lambdas are at least giving us a little peace of mind that the fun facts are working out, and that means it's probably the right lambdas. Okay, so let's jump in here, guys. Let's do the lambda equals 6. Doesn't really matter which lambda you do first. Sometimes I like to do the repeated one first, just because I'll be able to determine if there's any, if it's defective or not right away. So when lambda is 6, I'm going to do a null space of the matrix that I get when I subtract 6 off of that main diagonal. So if I subtract 6 off of the main diagonal, I should get something looking like this. So -1, 0, and 7, 0, 0, and 0, and 1, and 1, and -7. Now, this matrix can never be invertible. You have to be able to cross off a row. If it's a row of all zeros, that's the one you're crossing off. Okay, you don't get to make any more choices, just that one. And now I would just do an ERO or 2. I'll move the bottom row to the top, and I'll move the top row to the middle. The all zero row should always be put way at the bottom. And let me just add the first row to the second row. So I'll leave the first row the same. I'm going to add the first row to the second row. And here we go. We get pivots like that down the diagonal. And I do have a free variable here, but I think of my variables as x, y, and z. The z is free. Let me call that one t. Okay. But that's the only free variable I have. If I go looking at the second row of this matrix, 1 times y is 0. When I say is 0, that's because we're doing null space. Anytime you're talking about a null space, you're setting the equations equal to 0. So this second equation, guys, is just 1 times y equals 0. This first equation is 1 times x plus 1 times y minus 7 times z equals 0. Make sure you understand that conversion. From the matrix back to the equations is really important. There's always some students, I don't think anybody in here, but there's some people in the class who even at the end of the semester don't quite get the connection between the matrix and then the system of equations, which is really a chapter 2 issue. So we need to have chapter 2 totally solid. And in this case, that allows us to solve for x, y, and z really easily. So y is equal to 0. And now as soon as y is equal to 0, then x is equal to 7 times z, which is just 7t. And I can get my vector by just busting out my variable here, 7, 0, and 1. But the bad news is that this matrix is defective. This matrix is defective because the eigenvalue of lambda equals 6 had a weight of 2. It was a weight of 2 and only gave us one eigenvector. So we are talking about a defective system. I can write down one solution, and I should do that. Before I go on, I will write down, at least I can write down the first solution, which would be x1 of t equals e to the 6t times the vector 7, 0, 1. Okay? By the way, which flavor of defective system is this? It's the mixed eigenvalue type. I actually went easy on you guys last week. The defective system on the midterm was the regular defective case, which was, in my opinion, is the easiest one to deal with, and people did really well on it. But this one is a little harder. This is the mixed eigenvalue case. So I'll just add that here. This is mixed eigenvalue. And then the third one that I also did not have on the midterm, so you better be especially ready for the final on it, is the super defective case, which is the one with the W3, 4, and 5. Right? So it's very likely that I would ask another one of these this week, maybe not the same case as last time, but mixed eigenvalue would be one of the other options. Okay, so there's your first solution. From here, we need to create a second solution using those W's. So I always like to just get the diagram drawn for myself because it helps guide me in what I'm going to do. So the W's, we have a W1 and a W2 going to 0. We have a minus lambda I is what you're multiplying by here as you go across. And so this is going to be the form of it. And we're going to choose W1 right here. And it needs to survive the first power of a minus lambda I, which is actually this matrix, right? So a minus 6i is the matrix -1, 0, 7, and then 0, 0, 0, and then 1 and 1 and -7. It needs to survive this matrix, but it needs to not survive the square of the matrix. So what is the square of a minus 6i? Well, we have to work that out. So -1, 0, and 7, 0, 0, and 0, and 1, and 1, and -7 times itself. And I totally get it, guys, that it, there's so many calculations here. There's always a chance that you would just make a silly mistake. I will try my best to follow your work through. If you make a silly mistake, instead of like just erasing the whole thing and not turning in something for yourself, just try your best to do what you can with what you have. If you've made a sign error here in this calculation, you end up with the wrong matrix, and then that gives you the wrong W or whatever, right? You can live with that. You can live with that. I'm probably gonna, I mean, because I'm gonna look at the student and I'm gonna say, you know what, they know how to do the process. If they actually had a computer they were putting this into, they wouldn't have a mistake at all. It would be perfect. And so, and that's really what's important in the real world. So you have to trust me that I'm gonna be pretty nice to you on that as long as you have the work down onto the paper. Let's multiply this out, okay? The middle row is definitely gonna be all zeros. You can see that pretty quickly. But the top left corner is 1 plus 0 plus 7, which is 8. And then the top middle entry is 0 plus 0 plus 7. And the top right entry is -7 plus 0 minus 49. Oh my gosh, that's -56. Now let's go to the bottom row. -1 plus 0 plus -7. That would be -8. And then the middle entry is 0 plus 0 minus 7. And the bottom right corner is 7 plus 0 plus 49, which is 56 again. So I am looking for a W1. This is why I say the mixed eigenvalue case, in my opinion, is probably the hardest case, because I have to choose a W1 that will survive this matrix, but which will not survive this matrix. There will be many right answers, but it does involve a little bit of thinking. In this case, it's not as obvious as it would be in the super defective case or in the regular defective case. I have to work a little harder here. Anybody want to propose a vector that would survive the first matrix on A minus 6i, but not the second one? I'll give you a little something to chew on. The vector 7, 0, 1 does not survive this matrix, because if you put 7, 0, and 1 here and you multiply it out, 56 plus nothing minus 56. 0, 0, 0. -56 plus 56. This would be completely zeroed out. That sounds like that's a winner. It's a vector that does not survive this matrix. But actually, this vector is not a winner, because this vector doesn't even survive this matrix. In fact, that vector was the original eigenvector that we had used before we got started on this whole W process in the first place. So this one doesn't work. Can somebody think of something to try that would work? Caesar, do you want to give something a try?
About 1, 0.
1, 0, 1. So if I put 1, 0, 1 here, I don't think so. 1, 0, 1 is going to give me 8 minus 56. Remember, this vector needs to not survive this matrix. It's already surviving. Anybody else want to try? Which way?
1, 0, -1.
1, 0, -1. If I put 1, 0, -1 here, 8 plus 56. Sorry, it's got to be 0, 0, 0 at the end of the day. Oscar.
0, 1, 0.
0, 1, 0. I put 0, 1, 0 here. Then I will get 0, 7, 0. Anybody else want to crash and burn? Aaron.
0, -8, 1.
0, -8, 1. It sounds a little more likely. Let me try that one. 0, -8, and 1. Oh, sorry. No. 0, -8, -1?
Yeah.
Let's try it. So this is 0 minus 56 plus 56. Okay? 0 plus 0 plus 0, that works. 0, 56 minus 56 is 0. So that's looking good. Now, I do need to make sure that it will survive this one, though. So I'm going to bring it up here and test it here. If I put it here, 0 plus 0, ooh, -7. 0 plus 0 plus 0. And 0 minus 8 plus 7, which is -1. That is awesome. That is awesome. This vector, this vector for W1 survives the first power of the matrix, but not the square of the matrix. So it's exactly what my diagram requires. And what is W2? The W2 is actually this vector, right? Because that's what you got when you hop across this diagram. You're doing this matrix multiplication to get your W2. So your W2 would be -7, 0, and -1. So guys, it took a little bit of work, but we came up with something. What do we have here? We have e to the 6t times W1, which was 0, -8, 1, plus t times W2, which is -7, 0, and -1. Put a box here. That would be a good choice for x2. It's not the only, this is not the only choice of W1 that would work. But it would certainly be one choice that would work. Yes.
W1 negative 8.
Oh, yes. Sorry. The W1 should have a -8 and a -1. Thank you. Yeah, sorry. That's absolutely right. At least I did it correct in the calculation. Yeah, thank you. Okay, so that's it. And so does everybody remember this? This is e to the lambda t times W1 plus t times W2 right here. That's what we have. Okay. Sweet. So that's my second solution. Now I still need to do my other eigenvalue. These problems do take a little bit of time, don't they? My other eigenvalue is -2. That one is definitely going to pull its weight. It's just a matter of coming up with the eigenvector. So let's do that. So if I take lambda to be -2, that's my third lambda. I'm going to have a null space again. So I'm kind of back to the beginning here. I got to do another null space. This time I'm going to add 2 to the main diagonal of my matrix. So 7, 0, and 7, 0, 8, and 0, and 1, and 1, and 1. Now remember that you can always cross off a row. I always recommend crossing off a row that you don't want to deal with. The middle row is really nice because it's got a lot of zeros in it. So keep the middle row and cross off one of the other ones. I might cross off the top row, get rid of those 7s. And then if I want to just permute it over, I could do that. 1, 1, 1, and then 0, 1, 0, and 0, 0, 0. So I can divide through by 8 and move the bottom row to the top. Awesome. So we've got our free variable here. Sorry, we have one free variable, which is z. So z is going to be, I'll call it t. And y is equal to 0 from the second row of the equation. And then from the first row of the equation, x would be -t. And so I can make my vector by busting out the t. I get -1, 0, and 1. And so what is my x3 of t? x3 of t is e to the -2t times the vector -1, 0, and 1. So this would be my third solution, just like so. So I've got x1, x2, and x3. As long as you've written those down, as you guys know, you don't need to rewrite them ever again. You can just go for the general solution. You can just write x of t equals c1 times x1 plus c2 times x2 plus c3 times x3. Just going to be like that. And you're good to go. You've already done all the other work. Sorry, one more comment over here. Just a reminder that this W2, this last vector before you hit 0, this will be an eigenvector. So it should look like whatever the eigenvector was that you originally came up with. Now, it's not the same vector here, and you shouldn't change the W2. I actually saw a few people did that on the midterm. I think the vector that showed up on that one defective problem was -3, 3, and 6. And I saw a lot of people do this, which really brought out my gray hairs. First of all, these are not equal to begin with. There shouldn't be equal, and also you can't change the vector. You have to live with whatever the W2 was that shows up in the calculation. So I think on that midterm, probably 5 or 10 people just change the vector at the end there, and you should not do that. Yeah, just leave it the way you find it and you'll be good to go. Okay, so that's a mixed eigenvalue case. I would strongly recommend, since we already did a regular defective one on the last exam, I would expect this final is probably either gonna have a mixed eigenvalue or a super defective one. I might not do a super defective one right now, but that's the one where you have a W3, 4, and 5 as well. And the matrix has the same lambda 3 times. So just make sure you can do those kind of problems. Okay. Let's come back over here and keep going. We're 2 hours in. I can't believe it. I don't think I really, there's certain things I don't feel I need to review that much because people did so well on them. Like the variation of parameters method, people were really good on that on the exam. So I might skip that. Let's do, oh, I probably should review the kernel and range again. That did not go quite as well as I thought. But before I do that, I'm going to do another problem off of an old final. Solve for x1 of t and x2 of t. I'm going to actually write these out. So x1 prime of t is equal to 2x2 of t. And x2 prime of t is equal to negative x1 of t plus 3x2 of t plus e to the 7t. Okay. So this is obviously differential equations. Let's talk about the flow chart. Is this a single differential equation or is it a system of differential equations? I see more than one unknown function, so that should suggest that we're talking about a system. And so this is a system of differential equations. Is it homogeneous or non-homogeneous? Is there a b vector here or no b vector? So I kind of made it tricky because I didn't already give it to you like in the matrix and vector form. But what you're looking for, guys, on that b vector, you're looking for some term that's hanging off of the end that doesn't have the x1 or the x2 on it, which is what you have right here. This is a non-homogeneous system. So this is a system that is of the form x prime equals ax plus b. It is this type of problem that we're trying to solve. This is what we learned how to do just on Thursday. Just on Thursday. So I would like to just do one of these again. I know you just did homework on it. But I've already promised you I'm going to put one of these on the final. So might as well totally make sure we're solid. Okay. So the first thing I would do on this type of a question, guys, is I would get it set up with the A and the B. Right. So can somebody tell me, like, so this is going to be x prime equals, and then there's going to be a matrix A here, and then a plus a B vector here. Can anybody tell me what are the entries in the matrix of A? We have to be able to do this. Aaron? 0 and 2 on the first row, and what about on the second row? -1 and 3. Exactly. There was a problem on your midterm where I also laid it out as separate equations and you had to put the matrix together. There was a few people who did not put the matrix down correctly. They transposed it, which really can get you into trouble. So you need to just literally put these, for the first equation, you just put the coefficients horizontally. And then on the second equation, you put them horizontally into that second row. What is my B vector going to be here? My non-homogeneous piece? Somebody besides Aaron. I want to hear from somebody different. What's being added off on the end of these equations? Caesar.
Is it 0 and then e to the 17?
0 and e to the 7 times t. Absolutely. Exactly. So there you go. That's your B vector. Looks good. This is A right here, right? This is the B vector right here. Okay. With that said, let's see if we remember what we learned on Thursday. There is a 3-step process for solving the system. In step one, we ignore the B vector completely and we just work on the matrix itself. So I'm going to find my eigenvalues, subtract lambda off of the main diagonal. It's the first step. If I subtract my lambda off of the main diagonal here, I'm going to get a negative lambda and then 3 minus lambda and then plus 2. Okay. And then I'm going to get lambda squared minus 3 lambda plus 2. And that does factor. This is going to factor as lambda minus 2 times lambda minus 1. And so I'm going to get my lambdas to be 2 and 1. Even on a little 2x2 problem, guys, even on a 2x2 problem, you should check those fun facts, right? The trace of my original matrix A, the diagonal values adds up to 3, and my lambdas add up to 3. And also the determinant of A is 2, and the product of my lambdas is 2. So you always want to do that, guys. You always want to check that one. Okay, so these lambdas are looking good. Let's do our null spaces to find the eigenvectors. So I have to, for the lambda equals 2, I'm going to subtract 2 off of the main diagonal, and I'll get a negative 2 and a 2, and then a negative 1 and a 1. I'm going to just wipe out the first row of that matrix, just cross it off. And then I'll use my little AB trick on the second row, and that means I swap the two values and do a sign change. So let's use 1, 1, just to make the numbers nice. And so my first solution, my x1 of t, is e to the 2t times the vector 1, 1. Super. Okay. Now let's do the other eigenvalue, which is lambda equals 1. Again, I have a null space that I have to look at. If I subtract 1 from the main diagonal of the original matrix, I know I'm going a little fast here, guys. If I need to slow down, just let me know. But negative 1 and 2, negative 1 and 2, it's just two rows that are basically the same. I'll cross one of them off. I'll do my little A-B switch trick here as well, and I'll write down the vector 2 and 1. And so my second solution becomes x2 of t equals e to the t times the vector of 2 and 1. Just like that. Okay. Give you guys a chance to catch up here. I'll erase a little bit. Okay. Any questions so far? Those are my first two solutions. Of course, I can go ahead now and write down my complementary function. So on Thursday, I denoted this as the x sub c of t. And this just becomes c1 times e to the 2t times the vector 1, 1. And then plus c2 times e to the t times the vector 2 and 1. Go ahead and put a box here, so that that's easy to find later, if we need that, okay? So there's the end of the first step. So far, nothing's been too hard. We have had, it's a non-defective matrix. There's, no imaginary numbers, to deal with here. So all of that makes it pretty nice. So the next thing to do, guys, is the step 2. I just want to practice that with you real quick if I could. So for step 2, I have to find a particular solution. And I'll just remind you the way that that would look. Let's say that you get stuck somewhere and you're like, you can't quite finish the problem. Write down what you do know. We do know, we learned this on Thursday, that the form of the particular solution is going to be capital X times U. And then there's an equation for U. Might as well write that one down as well. U is the integral of the inverse of capital X times B. So these are the 2 equations. Again, if you need to use some flashcards to kind of get these into your mind, that's totally reasonable. These are the 2 new equations from our lecture on Thursday. And we just have to basically grind it out now. I always like to start this step off by just writing down the capital X, the fundamental matrix. And what is that matrix? This is the matrix that you build out of the 2 original solutions in step 1. So the first solution is e to the 2t times the vector 1, 1. You do need to shove that e to the 2t into the slots so that it comes out in the entries of that column. So e to the 2t, e to the 2t. And then in the second column, I shove the e to the t in with the vector of 2 and 1. So I just get my capital X like that. So I like to write that down. And remember, this is a bit of a journey to get to the answer here, but all along the steps of this journey, I'm looking for every partial credit point I can give you. So you'll get credit for writing that down, right? And then if you go to the next step, you'll get even more credit, right? The inverse of the fundamental matrix. That's usually, I need to find that because I see it in the formula for U here. So the inverse of capital X. Now this is a 2 by 2 matrix. I think I pretty much told you on Thursday, I'm going to stick with 2 by 2 size for this kind of a question. I have to do the little 2 by 2 determinant formula here, right? So this is e to the 3t minus 2e to the 3t, which actually comes out to a negative of e to the 3t. That's what we would have for the reciprocal of the determinant. And then you have to remember how to get the inverse of the entries themselves. So I should just actually write it down for you again. I know I wrote this on Thursday, but it's not really possible to overstate this. So let's just write it again. So we just need to swap the diagonal values and put minus signs on the off diagonal values. So swap the diagonals and do minuses on the off diagonals. And just be very careful as we go here to not accidentally make any mistake. Okay. So that's my X inverse. And you can leave it like this, or you can put this scalar into the slots of that matrix as well. It doesn't really matter. I guess it's not going to make it any messier if I shove the negative e to the 3t into the 4 corners of that matrix. It's going to change all of the signs and it's going to divide by e to the 3t. So this will become negative of e to the negative 2t in the top left corner, right? The top right corner, the minus signs will cancel and I'll get 2 e to the negative 2t. I'm just simplifying. That's all I'm doing right now. I'm just simplifying the X inverse. On the bottom row, e to the 2t divided by e to the 3t, well, that's e to the negative t. And on the bottom right corner, it would be negative of that same thing. So there's your inverse of your fundamental matrix. Okay. The next thing you're gonna wanna do is, because you have to take x inverse times b, we should now, finally, we're ready to use the b. We haven't talked about the b vector yet. I'm gonna use it right now to take x inverse times b. Okay, so I'm gonna write down the x inverse matrix again, just copying out the 4 entries like before. There's my x inverse. And I need to multiply that now by the b vector that we had written down when we first kind of re-expressed the original problem. Okay. Now, I have to be able to just multiply this out. Okay, so I do my dot product matrix multiplication procedure. On the top slot, I have nothing, and then I have a 2 times e to the 5t. Right, e to the negative 2t combines with e to the 7t as an e to the 5t. And then on the bottom slot, I also have a 0, and I have a minus of e to the 6t. So that should be x inverse times b. Yeah, so far so good. Next thing we need to do is integrate this. There's a lot of steps here, guys, but actually that's another reason to really make sure you learn this well. Because if this problem is on the exam, which I've already told you there will be, it's going to be worth a lot of points. Because there's a lot of things to do here. So you want to get this problem down. It'll really help your score. So the integral of this is the next thing, right? I have to do the integral of, oh, this is what u is, right? So u is the integral of x inverse times b. So let's work this out. I have the integral of this vector that we just wrote down, 2e to the 5t and negative of e to the 6t. Yeah. Everybody solid on integrating this? Well, if we integrate e to the 5t, we just get e to the 5t, but with a 1/5. So this becomes 2/5 of e to the 5t. And then if I integrate here, same idea, the e to the 6t, when you integrate it, you have a 1/6 of e to the 6t. So you get the negative 1/6 in front of this, of the second entry. This is my u vector. Are you with me so far? What am I going to do next? Correct. I have to multiply it by capital X times the u to get the x of p. So let's do that. The x of p is just capital X times u. And that's coming from the box there at the beginning of step 2. So I'm going to take capital X, which was e to the 2t, 2e to the t, e to the 2t, e to the t, and I'm going to multiply it by what we just worked out right here, 2/5 of e to the 5t and negative 1/6 of e to the 6t. Just going to start crunching that out. And in the top slot, actually, if you notice the powers on the e, I have e to the 2t being multiplied by e to the 5t. That's going to give me e to the 7t. But then on this entry, I will also get that, because e to the t being multiplied by e to the 6t makes e to the 7t. So it's really just 2/5 added to negative 2/6 of e to the 7t on that upper slot. And then on the bottom slot, it's actually a similar thing. 2/5 minus 1/6 of e to the 7t again. Yeah. That's right. And so let me just come up here to try to finish this up. 2/6 minus 2/5 minus 2/6. Let's see. I'm going to do this in my head. So it should be 1/15, I believe. of e to the 7t. And then in the bottom slot, it's going to be 7/30ths of e to the 7t. You can take my word for that. If I got it wrong, I got it wrong. Doesn't really matter. That's not the real point. So that is your x sub p.
Talking about that not being the real point, if I just left it,
If you just
or like,
left it like that, I would take it.
what about the guy before that?
This one, I want you to multiply it out. Because that's part of the 250B is can you multiply vectors and matrices out? So I would care more about that. If you left it like this, that might tempt my red pen. But if you left it like this, I would totally be okay. Yeah. So this is x sub p right here. And so the final answer, don't forget to do step 3. Most of you did a great job of remembering that on the midterm. But step 3 is where you just add together the complementary function to the particular solution. And this you can just write like so. And you don't need to fill in the gaps of that at all. You can just leave it as that. And I will completely take that as an answer. So, okay. So far, so good. All right. I think I want to do a couple of theoretical problems. I'm only going to go at most another half hour. I feel like we've done a lot of good stuff. I'm certainly not covering everything. You'll take those sample midterms on the resources folder and you'll realize, oh yeah, there are some other things. But I feel pretty good that we've done a lot of good stuff. So let's just try something slightly more theoretical. So this is also off of an old final. Actually, if I could point to one question that went the worst on the midterm last week, it was one of the theoretical questions. And so I'm going to do one that's just like that right now. So here it is. So let's just consider the solutions S to the differential equation x squared y double prime plus 2xy prime minus 2y equals 0. And I'm just going to ask you which of these is a basis for S. And it's like a multiple choice question, except that there could be lots of right answers. So the first possible answer, I'll call it S1, is 1 over x squared, comma, x squared. And then the second answer, sorry, this does take a little while to write it out. 1 over x squared and x. And then the third one, S3, is just x and x squared. And then the fourth one is just 5x minus 1 over x squared and 2x plus 7 over x squared. And then there's one more. S5 is just the set of just x. I had one like this in the midterm last week, but this one was sort of throwing people off. This one sort of threw people off, so it's good that we talk about it here. So we're talking about the solutions to this differential equation. Now, they're not asking us to solve this differential equation. They're just asking us to come up with a basis for the solutions. And whenever I'm thinking about a basis, one of the first things I want to think about is, well, how many basis vectors should I be expecting? Does anybody have any idea about that? Two. Why is it 2? Because still, I don't know the right word, but y. Does anybody know what word she's looking for? For this differential equation? It's the order. It's second order, right? Yeah, this is a second order differential equation, and one of the, and it's homogeneous because it's 0 on the right hand side. One of our theorems, and this was a theoretical point that I made, is that the dimension of the solutions to your vector space, this is really important, guys. The dimensions of your solution space matches the order of the differential equation. So the dimension of S is 2 in this example. It must be 2. So when I'm looking at these possible bases, the first thing you should do is you should realize that some of those candidates, some of these options from S1 to S5 don't have 2 vectors in them. Look at S1. It's got 3 things in it. Well, that can't be a basis. It's too many vectors, right? S5 can't be a basis. It's got only 1 vector. So you can cross these off, and you can say too many vectors. And this one is too few vectors. It's not the right number. So we're using the fact that the dimension of the solutions of a differential equation is always matching the order of that differential equation. That's certainly something that we went over. Now I've got 3 other choices left here. And in these 3 choices, I do have the right number of vectors. So they at least have a chance to be a basis. I shouldn't just assume that they are, because just because they have the right number of vectors doesn't automatically make them a basis. They need to be Li, for example. And they also need to actually be solutions. Actually, you can tell that the vectors in S2 are not scalar multiples of each other. They are Li. The vectors in S3 are not scalar multiples of each other either. They are also Li. The vectors in S4, same thing. These 2 are not scalar multiples of each other. They're also Li. So I'm not going to have a problem with that. But there is the question of, do these things actually solve my equation? So let's just check it out. So let's take 1 over x squared, for example. And I'm just going to do a couple of quick plugins here. I'm going to take my differential equation in that box, and I'm going to plug in some of these functions that I'm seeing. So I have x squared times 2 derivatives of 1 over x squared, right? And then plus 2x times 1 over x squared with 1 derivative, and then minus 2 times 1 over x squared. I just want to ask, is it actually going to be a solution to the differential equation? That's a question. That's the question. If I plug 1 over x squared into my differential equation, does it even work? Yeah, so let's try it out. Well, I got to figure out a couple of derivatives of 1 over x squared. 1 over x squared is really x to the negative 2. If I was to take 1 derivative of that, I would get negative 2x to the negative 3. And then if I took the second derivative, which means I have to take 1 more derivative, I would get 6x to the negative 4. Let's just check that out. If I put 6x to the negative 4 there, and then I put negative 2x to the negative 3 there, and then this one is just 2x to the negative 2, does it cancel out, is the question. I'm actually pretty terrible with negative exponents. I don't really like them that well. I probably would rewrite this as 6 over x squared, right? And then this one, there's a 2 and a minus 2, so it's minus 4, and it's x times x to the negative 3. Well, that's an x squared on the bottom as well. And then this one, I would probably go back and rewrite it again as 2 over x squared and ask myself, is that 0? Sure is. 6 minus 4 minus 2 is 0, that checks. Okay, so that is a valid solution to my differential equation. By the way, if you're wondering, why didn't I just ask you to solve the differential equation? Why am I like giving you all these things to check? The reason is because we never learned how to solve this kind of differential equation. It would not be a fair question for me to ask you that. I mean, I suppose I could have said, oh, try solutions of the form x to the r, and then you could plug in here and try to solve for r. And r equals -2, r equals -2, turns out it would have worked. So you would hopefully have come up with that. But again, yeah, this is kind of not a differential equation that we have a lot of practice with. So you wouldn't expect me to be asking you an unfair question that's like asking you to do something you never learned how to do. So in this case, I gave you the solution 1 over x squared, and you just plugged it in and check it. What about x? I also see an x here and here as well. So there's x. Is that a solution? Well, we can try it. Take x squared and then times x with a double prime on it, plus 2x times x with a single prime on it, and then -2 times just x. Is that equal to 0? Ask this question as well. So it's the same differential equation, but now instead of 1 over x squared, I can try to just plug in x itself. What do I get when I take 2 derivatives of x? I get 0, right? And then what do I get when I take 1 derivative of x? It's 1, right? And then this is -2x. Does that cancel out to 0?
Yes.
Sure does. That also works. That also works. So x works. So 1 over x squared works. X works. So this is looking pretty solid now. These are Li. They both are solutions. It's the right number of solutions. That's going to be a basis. What else do we have to think about? There's a x squared option here. What about that one? Would that one work? If we put x squared here, so again, we just plug it in everywhere. Let's put our question mark again. Do we get 0 out of that? Well, okay, so 2 derivatives of x squared, that's just 2. And then 1 derivative of x squared is just 2x. And then we have a -2x squared here, so let's just check it out. Does that cancel out? 2x squared plus 4x squared is already 6x squared, -2x squared, that is not 0. So x squared, although it is Li, and it does make the set have the right size, it is not a solution. So that's a tricky one. That's a tricky one. S3 is not a basis. Even though it does have the correct number of vectors in it, unfortunately, one of those vectors wasn't even a solution to begin with. Okay. What about S4?
Can you say that S4 would be the basis for S, since we already tested 1 over x squared and x?
Right, both 1 over x squared and x already worked. We checked those. And what you're looking at here, guys, is just somebody made linear combinations of them. And that's just going to make other, remember, this is a solution set is going to be a vector space. So it's closed under linear combinations, closed under addition and scalar multiplication. So it's going to work that this will be a solution and this will be a solution. Absolutely. And you could choose to just plug them both into here again, but that would at this point be extra time that you don't need to spend. You can just use the fact that you already know that 1 over x squared is a solution, and so is x. And therefore, any linear combination of those is still a solution. So S2 and S4 are both going to work here. Yeah, it's a nice nice problem. It has a little bit of computational aspect to it, but it's also kind of theoretical, to be perfectly honest. So you have to know the dimension theory of vector spaces, of differential equation solutions. And you have to, of course, deal with Li and deal with that sort of thing as well. By the way, if this was a third order equation, then your basis would be required to have 3 solutions. And in that case, to test if they were Li, you would need to use the Wronskian. You would not be able to just say, oh, they're not scalar multiples of each other, so they are obviously Li. Remember, I still had a lot of people on this midterm telling me that, oh, my vectors were Li because they're not scalar multiples of each other, even though there was 3 vectors. The scalar multiples reasoning only works when there's exactly 2 vectors in your hands. If you have 3 vectors or more, you can't just say, well, they're not multiple. You can't glance at it. You absolutely have to do an Li check, whatever that looks like. In the context of differential equations, the Li check would be the Wronskian. In the context of earlier in the semester, the Li check would be lay the vectors into the columns of your matrix and make sure that there's no free variables. Right. So whatever the context is, that Li check does come up, and you definitely need to be ready for it. That reminds me. Well, okay. Yeah, so are we okay with that problem? Okay, well, let's keep going. I'm gonna just do a little more. I know I'm already past 5:30, but I'm gonna just go a few more minutes. Not gonna go too much longer. Hmm. I don't know if you guys were surprised or not that on my midterm last week, because I kept harping on it about this equation for eigenvalue, eigenvector pairs. It actually didn't show up on the test. I just ran out of room to put that on the test. I still had people writing it down on their paper. It was like, you said that so many times, it's going to be on the exam. And then I didn't get around to it, guys. But you know, when I don't get around to something on the midterm, what it means is, oh, might be thinking about it for the final. So I'm going to do one more example like that. It's a little different than what you've seen before. And let's just see what you think about this one. So I'll do another example. This is also off of an old final. So it's turning out I'm liking my old final questions better than the ones that are on the review session. So here's what it says. Suppose that V is an eigenvector of A with eigenvalue lambda, and V is also an eigenvector of B with eigenvalue mu. I use this mu Greek letter for that. Show that V is also an eigenvector of A squared minus 5BA with eigenvalue lambda squared minus 5 mu lambda. Okay. It's a lot of words. People get scared when they see these questions with so many words, but it's nothing that we've never not done before. It's the same kind of, it's in the same spirit of things that we've certainly looked at in the past. It's just a slightly different set of numbers here. What do you suppose you're gonna write down on your paper is the very first thing here? Thank you. Yes, so the thing everybody wrote down on last Tuesday and didn't get any credit for because it wasn't on the test. Maybe there'll be another chance, right? So AV equals lambda V. And would there be anything else we might want to write down at this stage?
B
B
or BV.
V
To go to mu V.
equals mu V. I did have some people, so like I said, I had a lot of people writing down AV equals lambda V last week, but you know what I also had, which I didn't want to start crying about it, but I saw stuff like this, you know. I saw stuff that just didn't make sense. I did even see somebody write this down, and that really got my red pen going. So you gotta be real careful here, guys. Make sure you have the equation correctly written down. Okay, so we wrote it down for A and then also for B. This would already get you a nice hunk of partial credit, but how am I gonna go to showing what we're being asked to show here?
You would like use
So
the
now we get into the meat of the solution would be to do what?
Would you use that equation, the a squared minus 5ba, and substitute it for like anything a with lambda v?
I don't want to just artificially put the lambda and the mu into the first step. Of course, it's going to show up eventually because we see that this is still there. But I don't want to force it in there. What I really want to do is I'm wanting to show that V, just V, right? That V is an eigenvector of this matrix still. So you should just put only the V there. All right. And then at this point, okay, we know that this is going to show up somewhere, but don't write it down prematurely. Let it organically appear as you do the calculation. So just go ahead and trust the math is going to work. So what I would do here, guys, is I would distribute this a squared v minus 5bav, right? So just distribute it. And does anybody else want to help me with the next step here? Go ahead, Oscar.
Would you take out the square?
So is this correct?
No, it's not.
So last week, I mentioned that this doesn't really make sense either because now you're squaring a vector, and that is something actually that doesn't make sense. We can't square a vector, and we never did learn how to do that, and it's because you can't do that. So that's not what you need to do.
Oh, split up the a and then convert one of the av's into the lambda v.
Yeah, let me just do it one step at a time, but that's exactly what you want to do, guys. Just take it nice and slow here. The a squared can be written as a v, and then you can start, if it helps you, you can put parentheses in here because parentheses don't hurt anything. So you can put those parentheses in there, and then so what Oscar is saying is that the AV can be changed to a lambda v. And I can do that over here on this second part also. There's an AV that can turn into a lambda v. And at that point, I'm literally just substituting from here. Okay? And what would you suggest that I do next here? I've got those lambdas now in the expression. What can I do with them?
Take out the lambdas.
I would pull them to the front. They're just numbers, right? I would just pull them to the front. So I'd have a lambda and then an AV on the first one. And on the second one, let me put the lambda next to the 5 and then a BV. We're getting there. I think we are getting there. So now I can just do the same thing one more time. I have another AV, so it's just going to become another lambda V. And then I have minus 5 lambda. And now here I have BV. So we just have to use the mu V for that part. Okay. This is a nice problem. I like it a lot. the v can be factored out of the backside, and I get lambda squared minus 5 lambda mu. Or I guess it was supposed to be 5 mu lambda. Of course, that doesn't matter because those are just numbers, so I don't care what order you write them in. But that is where you were hoping to end up. You have this is your eigenvalue times v that you obtained starting from the matrix times v. So this proves it. We're good to go here, okay? So yeah, so anyway, you guys seem to be really on top of this, but I just worry because, yeah, I think these can be, because of all the words, they can be a little bit scary for people, and that can be a little bit of an issue. I said that I was going to give you the Gram-Schmidt formulas on the front of the exam. What would you use those for? If I ask you what kind of a question? Those, if you remember, the formulas are something like W1 equals V1, and then the second Gram-Schmidt formula is W2. These are not the same W's that we just learned about last week. It's a totally different context. The W2 is, what is it, V2 minus some crazy formula with a fraction involving an inner product. What do we use those for?
Orthogonal, to find I can't pronounce the word.
To orthogonalize
Yes, there you go.
a set of vectors. Yeah. So if I give you a set of vectors and I ask you, if I ask you for an orthogonal basis for something, right? Or even an orthonormal basis. If I ask you for an orthogonal basis or for an orthonormal basis, you want to use the Gram-Schmidt formulas first. The normalizing always happens at the end. So you wouldn't do that until you've already orthogonalized the vectors first. But honestly, I'm going to give you those Gram-Schmidt formulas. As long as you're using them in the right time when you're supposed to use them, it's really hard to mess that up. It's a computation. And of course you could mess up the computation, but that would not be a big buster on your exam by any means. But yeah, so that's what the Gram-Schmidt formulas are for. Let me see. Just trying to see if there's anything else I want to go over.
Didn't you say you were gonna go over the?
Oh, the kernel and the range. Yeah, I should do something on that. I think I'm just gonna make up a problem. So we'll do one more problem on the kernel and the range. I mean, I do have something on the review sheet, but it's really. Well, we could use the one on the review sheet. We could use the one on the review session sheet. So let's do from the review session sheet number 5. Okay, I'm probably going to stop after this. I'm not promising I've covered everything, but we've certainly done a good amount. But I think we'll all be ready for a break. So on this problem, what I'm going to do, guys, is I'm going to define t going from m2 of r to r squared via t of a, b, and then c and d is equal to, and then there's 2 slots here, a minus b minus 3c, comma, 2b plus d. And I'm going to ask you a couple of things here. I would like to find a basis for the kernel of t and the range of t. And then second part, I would like to decide, is t one-to-one onto both or neither? So there was something like this on the exam, and it was the very first problem on the midterm this week, and some folks were pretty far off from what they were supposed to have. Guys, the kernel has to be a subspace of V. So when you're writing down your kernel, it should be looking like 2 by 2 matrices for the kernel. And then when you're doing the range is always a subspace of W. So the vectors should look like something in R2, 2 slots, basically. Okay, so that's the key. Let's start with the kernel. Oh, you know what? And even before we do that, what is the dimension of M2 of R?
4,
It's 4, right? What is the dimension of R2?
2.
It's 2, right? So notice that the V is bigger than W. Does that allow you to say anything about the choices here?
It's not 1 to 1.
Correct. It's not 1 to 1, and of course, then it's not both. There were still a handful of people last week who just crossed those off with nothing written down. Please give me an explanation. You could just say here, V is bigger than W. I will know what you mean if you write that. And then V is bigger than W. So if you write that down, at least I can justify it. If you just cross it off with nothing else written, it's really hard for me to just take that as an answer. So I need justifications on it. And it might be onto. So we'll leave that up in the air for now. But let's do the kernel here. For the kernel, remember that what you have to do, guys, is set this thing equal to 0. But it's 0 in whatever universe W is representing. In this case, it would actually be the point 0, 0. And so that means that if you just plug in what the formula for the t was, a minus b minus 3c, comma, 2b plus d, I have to set that one equal to 0 and 0. This creates a couple of equations. Let me write them over here. A minus b minus 3c is equal to 0. And 2b plus d is equal to 0. And now I have to solve for a, b, c, and d. And I would probably use a matrix for this. The first equation is going to look like this. Be careful, there's actually 4 unknowns. So that first equation doesn't have a d in it, but there should be a column for that anyway, because there's going to be 4 columns here for those 4 unknowns. The second equation has no a value, there's a 2b, and there's a 1d. So it's getting pretty close to a row echelon form before I even do any work on it. So what you can see here, guys, is that I do have 2 free variables. C and D are going to be free, so I'll use R and T for those. And then I have to solve for A and B. The second equation allows me to solve for B. The second equation is really just this. Solving this for B, I get negative 1/2 of whatever D was. So that's negative 1/2 of T. That's for the B variable. And then for the A variable, A is supposed to be equal to, if I solve for A, it's just B plus 3C. So B, which is negative 1/2 T, plus 3C, which is 3R. Okay, and so there you go. That's A, B, C, and D. The important thing now is that you put those variables into the right shape of what the kernel looks like, which is going to be 2 by 2 matrices. So I can go ahead and put this into, a 2 by 2 matrix. This is the key thing, guys. A lot of people make the mistake of just listing slots out, but it should actually be a 2 by 2 matrix. Okay. And then to get your basis, what are you going to do to get the basis? Bust out those variables, exactly. So the basis for the kernel of T is going to be, when I bust out the R, I'll have 3 and 0 and 1 and 0. And when I bust out the T, I'll have negative 1/2, negative 1/2, 0 and 1. That's your basis. 2-dimensional kernel, by the way. Interestingly enough, once you've done the kernel, you can now actually answer the onto question. Because, well, how can I answer the onto question if I've worked on the kernel? I thought the kernel has to do with one-to-one. So why am I able to answer the onto question from doing the kernel? Yeah, the general rank nullity theorem. This is really good, and people did a great job on last week's test on this. This is important. The dimension of V is the dimension of the kernel of T plus the dimension of the range of T. It's a really nice theorem. It's super helpful for these kind of questions. Yeah, so the kernel and the range, they add up to the dimension of V, which is 4. And we just did the kernel, which was 2-dimensional. So you can see that the range is 2-dimensional from that equation. How does that compare with W? What's the dimension of W? 2. And the dimension of the range was 2. They're the same, right? That's what onto means. So it is going to be onto.
So if it was neither, would one of the dimensions be greater or less than?
Neither is always on the table. Whether V is bigger than W, less than W, or even equal to W. Neither will always be an option, one of the two options that could happen. So neither comes up a lot because of that reason.
In this like problem, how can we, I guess, in what scenario would neither be like the answer?
It would be neither if I change this to this again. I put that in that second slot now. Now it's going to be neither. In this scenario, your kernel will go up to 3-dimensional, and the range will be 1-dimensional, and you'll have 4 equals 3 plus 1. And in that case, still not 1-to-1, but now it's also not onto in that case. But because I picked a different expression here, this actually helped cut down the kernel to be only 2-dimensional, which made the range go up to 2-dimensional.
So if like the dimension of range is greater than the dimension of the kernel, then it's neither?
No. The dimension of the range versus the dimension of the kernel has nothing to do with it. It's all going back to comparing with W. So for the onto, I have to compare with W, which is 2, with what the dimension of this range is. But what I'm saying is that the kernel can affect this number. Like if the kernel goes up to 3 dimensions, then this would go down to 1. But to decide if it's onto, I'm still comparing this number with that number to figure that out.
No,
Awesome. So, yeah, Cecil.
it sounds kind of silly, but if when you change your number to the same exact thing,
Yeah.
that's still two-dimensional, right? Because there's 2 slots.
Well, the W is still the same.
But I'm saying they can be the same, and that is.
Oh, yeah. But if they're the same, your range is not going to be as big. It would be only 1-dimensional. Why would that be? Just chase it through. Trace it through. If I change that second slot, then my second equation is just that, right? So then my second row of my matrix is just that, right? Well, then in that whole row gets crossed off. I only get this pivot. I have 3 free variables. So my kernel would be 3-dimensional. I'd be using R, S, and T over here. I'd have a 3-dimensional kernel. And if I put a 3 here, then I'm putting a 1 here, and that's not matching W anymore. Now, incidentally, we found our basis for the kernel. There's also the question of what is the basis for the range. Really do have to go. Really quickly, normally the way you do the range is normally the way you do the range of T is you take the span of T of a basis of B. So I would do, and people did a good job. This would be T of 1, 0, 0, 0, and T of 0, 1, 0, 0, and T of 0, 0, 1, 0, and T of 0, 0, 0, 1, right? If you work those things out in this example, like T of 1, 0, 0, 0, if I put a 1 for A and 0 for everything else, I'll get 1, 1. Okay, notice that the range is consisting of 2 slots. It's part of W, right? What is T of 0, 1, 0, 0? Oh, I've got to go back to what this was before, sorry. This was a 2, oh, I've screwed this up. I'm so sorry. This, going back to what we had before, I don't want to mix the problem up. This was a 2B plus D. So when I plugged in A, I should have gotten 1 and 0. Sorry about that. And then when I plug in 1 for B, I get a -1 and a 2. And then when I plug in a 1 for C, I get a -3 and a 0. And then when I plug in a 1 for D, I get a 0 and a 1. Now, the thing is, I know that this is LD. There's too many vectors here. And I got to throw something away. You could set this up into a matrix. So the first vector goes in the first column, the second vector in the second column, the third vector in the third column, the fourth vector in the fourth column. I'll augment that with zeros. This is already giving me pivots in the first 2 columns, which just means I'm crossing off the third and fourth columns, and my basis would just be just these 2, right? So I would keep for my basis for the range, I would just use 1, 0 and -1 and 2. And that fits because this was 2-dimensional, this was 2-dimensional, all right? And too many hypotheticals going on here. I didn't get it all fixed back up again. But that would be it, right? But I do want to make a quick comment. Because it was onto, when I'm asking you for a basis for the range of T, I might as well be asking you for a basis for W. Because after all, onto means, the very definition of onto is that the range of T equals W. So if you know that your transformation is onto, and somebody's asking you for a basis for the range of T, you could just as well imagine, oh, I really just need a basis for W. And if you look at what your W is, R2, probably the most natural basis for R2 that anybody would ever think of is this one right here. Yeah. And this would also be a correct answer. Actually, you see those vectors here. Actually, if you picked any 2 of these that were not scalar multiples of each other, you'd be good. Because you know the dimension is 2. And these are all good vectors for your range. So just pick 2 of them. You could actually do that. Nothing says you have to go put it in a matrix and circle your pivots and throw away the unpivoted columns. You could just look at this and say, I just need 2 of these vectors that are not scalar multiples. I'm going to spend my $2,000 on this basis for the range. And as long as I don't pick 2 scalar multiples, I'm going to be good to go. I would not pick the first and third one. Notice that the first one and the third one are scalar multiples of each other. That would not be a basis, right? Your basis always has to be Li. So, but what I'm just trying to say is this would be perfectly fine as an answer. But if you wanted to make your life even easier, you could say, oh, it's onto. So the range is just R2. And I know just basically without even taking a breath that this is like the easiest basis for R2 in the whole world. Yeah, so one of the reasons why, I'll give you a quick little insight. One of the reasons why I keep this kernel range thing for the third midterm instead of kind of putting it with the second exam is it forces people to still remember basis and dimension concepts even when studying chapter 6 for the third exam. And that way you're actually reviewing linear independence along with that section as well. So I'm hoping this is still somewhat fresh, but this did not go great on the exam, mostly because people were not even writing kernel vectors that were in B and range vectors that were in W. People were getting all mixed up. They were putting polynomials on part B and matrices on part A, and it was supposed to be the other way around. And it was really, I was like, okay, this is still not quite where it needs to be. So I think this was good to do this problem today. You're going to see something again on this coming final exam about linear transformations. There's another question I could ask here. I don't have time to go over it now, but I'm just going to ask it, which is to simply to show that T is linear. This actually was something from section 6.1, which is where we, before we learned about the kernel and the range, you have to show that T respects addition and scalar multiplication. Make sure you know how to do that as well. I am sure that there's some examples of showing that T is linear in the sample exams. So I'll let you work on that and we'll kind of go from there. But I'm going to be in big trouble with my dinner date if I keep talking much longer, because I've got to meet them at about 6:15. So I'm going to call this good. I'm going to go to dinner. I'm going to be back to my office by 8. And I hope that this was helpful. Good for now? All right. Thanks, guys. Appreciate you coming.